Hello everyone. Okay, so in this video we are looking at the area under a curve. So integration can be used to find the area under a curve. By under a curve, we are referring to the area of the region between the curve and the axes. When finding the area, we use bounds on the x-axis, i.e. bounds on the region we are considering. So I have this little region here. I want to find out the area of this function here, right? This bluish area, I don't know if you can see it, but area A. And all you do is I integrate my function between A and B. That's it. I integrate my function between A and B. Sorry. So let's go to GeoGebra here and I'll show you how we kind of came up with this. So here we are. And we can get an approximation for the area under a curve, like using rectangles, right? Like trapezoidal rule even. But so if I made one big rectangle here, I can make an approximation, right? It'd be 5 times whatever the height is, like 7, like 35, right? But what if I increase the amount of rectangles? So say if I increase the rectangles now to like 10, right? So I make all these rectangles here. And find the area of each rectangle. Now my approximation is getting closer and closer to what the actual area is. Now, if I keep increasing these strips to where the width is like so small. Look at here. If I keep adding and adding more, right? The closer and closer I get to my actual answer. So let's go back here, right? Then the deal with that is, right? I have a curve. This is where we kind of came up with the idea for integration, right? So I have a curve here. Ding, ding. I am now splitting it up into an infinite amount of rectangles. And you just have to think, right? Here's one of them here, right? Now, it would be like a million times smaller than that. But I'm going to say the width of this rectangle is just the change in x, dx. And then the height of my rectangle is going to be f of x. So what I do is I use my summation notation. So if I sum all of these areas, which is given by f of x times d of x, right? Because length by width, get the area. And I do that between A and B. And I do that between all the values of A and B. Now, the thing with summation notation is that is kind of more for, it kind of, it just goes like boom, 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 like ups like in 1 or 2 or like kind of distinct amounts, right? So if I am finding an infinite sum, so I'm literally getting every possible value between A and B, that is when this sigma notation becomes my integral notation, right? And the integral then is born here like that. So it is like the summation notation, but it's just a lot more smoother out. And I like to think it's kind of more smoother out because I'm like taking every value. I'm not going like going up in 1s or 2s or etc. That is where it kind of comes from there. If I made an infinite amount of rectangles and I'm summing all of them up between A and B. So let's look at an example question here. So 2022, the diagram below shows a graph of the function ax squared plus bx plus c, where a, b, and c are integers. The 3 regions of the diagram are marked, k, l, and n. Each of the regions is bounded by the x-axis. The area of region K is 538. Use integration of f of x to prove this. So, region K, so if I integrate between 2 and 0 of ax squared plus bx plus c, I'm going to get here between 2 and 0. So, ax cubed all over 3 plus bx squared all over 2 plus cx is equal to 538. So I know that the area here is equal to 538, right? So I don't need to think about that. So I know the area in here is equal to 538. So evaluate it here. I have a times 2 cubed over 0 plus b, oh, that's 0, so over 3. I do apologize. Plus b times 2 squared all over 2 plus c times 2. And then minus 0, whatever, sub in 0 here, that'll go to 0, that'll go to 0, that'll go to 0. So I'm just subtracting 0 here, is equal to 538. So, do apologize. Right, so 8a over 3 plus 4b over 2 plus 2c is equal to 538. I am going to, first of all, 8a plus 2b plus 2c, so 8a over 3 equals 538. I'm going to multiply across by 3 here. So I get 8a plus 6b plus 6c is equal to 538 divided by 3. 1614. And then I notice I can divide everything here by 2. So I'm left with 4a plus 3b plus 3c equals 807. And that was what I was asked to prove there. Right. 2020. Let h of x equal a half ln 2x plus c, 2x plus 3 plus c. Find the derivative. So the derivative of ln is going to be, so it's going to be a half times ln goes to 1 over what my ln is, 2x plus 3, and I multiply by the derivative in here, and the derivative of 2x plus 3 is 2, and then the derivative of c goes to 0. So my answer here is going to be a half times 2, it's going to cancel out. 1 over 2x plus 3 is my derivative. Now, the diagram below shows part of the diagram, shows part of the function h of x. The shaded region in the diagram between the graph and the x-axis from 0 to a is 3, is ln 3 square units. Find the value of a. So the area under this curve is equal to ln 3. Well, the integral of h of x, well, we know what that is because it was given to me up here. A half ln 2x plus 3. A half ln 2x plus 3. And plus c, but we're doing my definite integral, so I don't need it. So I'm doing that between 0 and a is equal to ln 3, the area of the curve. So that is going to be a half ln 2a plus 3 minus a half ln of 3 equals ln of 3, because 2 times 0 is 0. Multiply across by 2. So ln 2a plus 3 minus ln 3 equals 2 ln 3. Bring over the other ln 3. So I'm going to have ln 2a plus 3 is equal to 2 ln 3 plus ln 3 is 3 ln 3. Ln 2a plus 3 is going to be equal to ln of 3 cubed. So I'm using the rule here. A ln x is equal to ln x to the power of a, which is going to be 27. Therefore, 2a plus 3 equals 27. 2a is equal to 24. A is going to equal to 12. Right. And I'll leave it there for this video. I hope this video was some help to you guys. And I'll catch you guys later. Bye.